Okay, so omega is a scalar form on a fixed. Now recall, I am sure it has been said many times, Higgs bundles. So you have E and theta. E is a holomorphic vector bundle on X. Holomorphic bundle. Theta is a section of holomorphic cotangent bundle omega X such that theta waist theta is 0. There is some stability condition, semi-stability condition, which I will not recall. Just to say that you can define degree of a shift by dimension of X, C1 of F, omega to the power dimension of X minus 1. So this is the degree of a shift. Now use by stability means degree by rank of any subshift is less than or equal to degree by rank of the total shift. That's semi-stability condition, and strict inequality stability condition. So, and polystable means direct sum of stables. So E holomorphic vector bundle theta is a Higgs field. You throw in the condition polystability. Then you put some topological condition, C1 of E is equal to 0 is equal to C2 of E. You put all these conditions. On the other hand, you have representations of pi1 of X from pi1 of X to your favorite group, take SLNR, you can take GLNR, SLNC, GLNC, whatever you prefer. So let me put GL because SL is contained in GL. GLNC. Now we put some irreducibility condition. That means you take homomorphism such that the image, consider the image of the homomorphism, take a homomorphism pi1x to GLNC. Now GLNC acts on Cn, the tautological action, the standard action, which is technical term is the standard action. So pi1 of X acts on Cn by this homomorphism. Once you fix a homomorphism from pi1x to GLNC, and you say that it is completely irreducible means it's direct sum of irreducible representations. So I am considering completely reducible representations. And now GLNC acts on the space of representation because GLNC acts on itself by conjugation. So it acts on homomorphisms with the same action. So I have this space. So now non-abelian correspondence says that if you put the rank of E is R, N, then these two are naturally bijection. So now let us, we need, this is the non-abelian correspondence. So now we need some, this has been, I am sure, talked about many times in the last week. So even today it was mentioned a couple of times. So let me now recall some properties of this, very important properties which will be used. So property number 1. See this, as you seen in the lectures, this correspondence is done via harmonic map. A Higgs bundle gives a stability, polystability condition, produces a harmonic map, or in this case, but that was done by Simpson and Karp case Hitchin. And here, the harmonic map was constructed by Correlate in a general case, and the special case of Riemann surface by Donaldson, which was lectured on this morning. So this correspondence is via harmonic map. We have harmonic map. So it depends on the, of course, harmonic map depends on the metric. But this correspondence doesn't, is independent of the metric. It doesn't see the scalar form. In particular, it's a non-trivial theorem that if it is for one scalar form, this is one such omega 1, it is polystable, then any other it is remains polystable. For other Chern classes, it is not true. If you remove this condition, then it is not true. It depends. Polystability depends upon the polarization, the scalar form you choose. But in this case, it doesn't depend on the scalar form. This is, though the correspondence uses the scalar form, this final bijection doesn't depend on the scalar form. So that's one thing. Next thing is independence. Of omega 2, which is equally important. M is a smooth projective variety. So by smooth projective variety has many complex submanifolds. So you can smooth projective variety means it is embeddable in some PED projective space, and then by general hyperplane you can get cut, you can lower dimension and keep getting. So it has many all dimension, lower dimension, all huge number of submanifolds, complex submanifolds. This correspondence is compatible with submanifolds. What I mean by that? In fact, it is compatible with pullback, much more than that. Anyway, it doesn't matter. Let me just say it was submanifold, which I will be using, though this actual statement is stronger. So M, so suppose X, and suppose I have a submanifold M. So now we have Higgs moduli space, Higgs bundles, Higgs on X, and I can restrict to, if I Higgs bundle E theta on X, I can restrict to the submanifold. So from that, I have maps to Higgs on M. Similarly, I have a representation of the fundamental group of the pi 1 of X, rep pi 1 of X. I'm not writing that UR prime. Similarly, restrict this fundamental group of M to fundamental group of X. There's a natural map given by the inclusion of this complex manifold. So if I representation of homomorphism of pi 1 of X to GLNC, I can restrict to composite pi 1 M to pi 1 X, and then using the representation, I get a map. Rep pi 1 of M. Now, non-abelian Hodge correspondence gives this here, this diagram commutes. This is highly non-trivial, this diagram commutes. Then let us see another property. Third, which is a generalization. I use that it is a projective variety, that means compact, it extends to non-compact case. So that means suppose D is a normal crossing divisor, suitable divisor on X. Then instead of representation of pi 1 of X, I can consider some bigger space, so pi 1 of X minus D. And representations of that. It can be much bigger, right? For example, CP1 is simply connected, so its fundamental group is trivial, so it doesn't have any representation of the fundamental group. But if you put some punctures, suppose you put n punctures, the fundamental group is a free group of n minus 1 generators. It is a huge representation space, right? So you can even if you very simplistic space like E1, whose fundamental group is trivial, you can allow choosing D suitably, you can make it very large. So in non-abelian Hodge generalization for the non-compact case, so this part is replaced by that pi 1 of X minus D, and this part is replaced by Higgs bundles with some extra structure on the D, same as before, but on the extra structure on the, which is called parabolic structure, generalized parabolic structure. I don't want to get into that. Defining them will take a lot of time. So I don't want to get into that. But what I want to say that it something like parabolic Higgs bundles on X with parabolic structure on D. So when you do that, again there is some bijection is there. Work of many people, but the final work, the complete work is done by Mochizuki. T Mochizuki, when you say Mochizuki, you have to be careful. Okay, now, so now, then let me say another property, the simplest case of non-abelian Hodge correspondence, the unitary case. There are some subcases of these two, so that this correspondence takes that subcase to that subcase, and that correspondence is quite trivial. So, but we need that, so I'm recalling it. So when you take, instead of GLNC, you go to the compact group, namely unitary group. So homomorphism pi1 of X to GLNC. Then what is the corresponding? Then what is the corresponding thing here? Suppose you start with the unitary representation. What is the object? Very simple. Unitary representation is a representation of a representation gives a flat connection, right? Because that maybe, is it everybody clear with that? That a representation of fundamental gives a flat connection. Maybe I can quickly recall. So so how pi1 X, let me put a 2 GL and C produce a flat connection. So I take X tilde, universal cover corresponding to point X, X naught. So pi1 acts on this is a quotient. Now I take X tilde across GL, Cn. Now GL, this pi1 of X acts on this product. It acts on this X tilde by deck transformation. It acts on Cn by the standard representation. Pi1 of goes to here by rho. And this rho and GLNC acts on Cn. So using rho, pi1 of X acts on this. So it acts on the product by the diagonal action. I go model the quotient. On the other hand, I can take just X tilde modulo pi1 of X naught X, which is just X. So this is a bundle, and this is a bundle with a flat connection. Because we started with a trivial bundle, X tilde across Cn. This is a trivial bundle with a trivial connection. By this action, the trivialization is destroyed, because trivialization is not preserved by this action. But constant section go to constant section. So the flat connection is preserved. So the quotient comes with a flat connection. It's a flat bundle. So that's how representation gives a flat bundle. So now, the unitary case. Suppose you start with an unitary representation. That means instead of GLNC, you take UN. Then by this procedure, you get a flat bundle on X, right? That's my E theta. Theta is 0 in that case. And what is the bundle E? E is a flat bundle. Flat bundle is also a holomorphic bundle, right? Flat bundle means transition functions are constants. But holomorphic bundle means transition functions are holomorphic. Constants are holomorphic. So flat bundle is a natural holomorphic structure. So you start with unitary representation. You get a vector bundle, flat vector bundle. That means holomorphic bundle. I'll put the theta to be 0. So you get a Higgs bundle. So this is the correspondence. Very simple correspondence. There is no complication in this case. Which you like, we use it. Okay, now what is the question we are interested in? Now let me try to state the question. Direction of the question, not exactly the question. Question I'll formulate it later, but Suppose you have a family of curves. Family of Riemann surface parameterized, holomorphic family of Riemann surfaces parameterized by T. T is a complex manifold, this is a complex manifold, this is holomorphic submersion, fibers are compact complex manifolds of dimension 1, compact complex connected manifolds of dimension 1. That means Riemann surface of some genus. So now suppose I have a flat connection on this. Representation of the fundamental group, which is same as a flat connection on this. Suppose flat bundle on this. That means given by some representation. And suppose the connection is completely reducible. So now what? Suppose fiber is completely reducible. So what happens? For each point T, I can restrict the flat bundle, right? Restrict the fiber. I call this pi. I take pi inverse of T. It's a Riemann surface, compact Riemann surface by definition. And E nabla is a flat connection on this, right? So now I can restrict it to this. So E nabla restricted to pi inverse T. So I have, let me recall again, XT over T is a family of Riemann surfaces, a holomorphic family. I have a flat connection, as that fiber-wise is completely reducible. Flat connection on XT, on entire XT. So for each T, I have pi 1, take the fiber, which is, I'm calling this my pi, so pi inverse T. This is a Riemann surface, compact Riemann surface. I'm restricting this flat connection to this. So by the correspondence, I get Vt theta T, Higgs bundle on Xt. So this is a flat connection. So this will give me by non-abelian correspondence a Higgs bundle. So for each T, I have a Higgs bundle. Now question, when this family of Higgs bundle moves holomorphically, when this becomes I have a family of Higgs bundles, right? For each T, I have a Higgs bundle, a C-infinity family of Higgs bundle. Question I'm interested in, this is a vague question, I'll make it more formal, more precise. Question is, when this family of Higgs bundle holomorphic? So that is a, first of all, even this vague formulation, let me give you some example where it is and where it is not. So now, again, I'm writing the same thing, Xt over T. Now suppose E nabla. Now I take nabla to be unitary. Right? Now for each T, I have this pi inverse of T for each point T in T. And on this, I have the Higgs bundle, V theta, Vt theta T. Now, from what I said, the unitary case, it's now clear that it's a holomorphic family, because what is the, I have a flat bundle, so I have a family of flat bundles, so a family of holomorphic bundle. And what is the Higgs field, Higgs bundle? The bundle is unchanged, the same bundle I'm taking. And Higgs field is 0. So 0 is, of course, a holomorphic function. And the bundle is, by definition, is a holomorphic family of bundles. So this is a holomorphic family. By tautologically holomorphic. Tautologically. Because this family of bundles, underlying bundle is the same bundle, the flat bundle, which is a global flat bundle. So it's a family of bundles. It's a flat bundle, holomorphic bundle on entire Xt. So on each fiber, it is by definition is moving holomorphically, right? When you call this moving holomorphically, when you put a global holomorphic structure, it's holomorphic. And the Higgs field, you don't have to check anything that the Higgs field is holomorphic because Higgs field is 0. Okay, so this is an example. Now let me give an example where it is not holomorphic. So I'll use some terminology which will be explained later, but just to give an example, I'm saying it. But it will be explained better. So this part, I don't know, it might not make sense. I take the Teichmuller space T. T to be the Teichmuller space. I fix a point T naught. On this, I have the universal family of Riemann surface. And I take the Fuchsian representation corresponding to this Riemann surface. So it gets a representation on x T naught, right? But inclusion of x T naught in T naught, x T naught, this is contractible. So this is a isomorphism of fundamental groups. A representation of x T naught will produce a representation of this. So I'll get a flat bundle on this. Because the fundamental group is same as fundamental group is this because T is contractible. The base is contractible. If I have representation of this, I get a flat connection on this, I get a flat connection on this because the fundamental groups are same. Now this has a representation, particular representation, I take the Fuchsian representation. So now I will not be able to explain this, but what are the corresponding flat Higgs bundles on points of T? Points of T Higgs bundle are of the form for each point T, which need not coincide, we'll get a the underlying bundle will be like this, k to the power half direct sum k to the power minus half. Because where k is a canonical bundle, square root of the canonical bundle, and Higgs field will be like given by some theta, it will be diagonal 0, 0, 1 theta. Theta is a not I should not say theta. Theta is the Higgs field. It is given by some omega alpha beta h naught of kx on the point x xt. Let us put xt or any t. This is the Higgs bundle in this, and beta is h naught of xt, k of xt. Now I have a family of Higgs bundles. So you understand, I take this family of Riemann, universal family of Riemann surface, I fix a point, I take the Fuchsian representation. This gives a flat bundle on xt naught. So these fundamental group are same, so I get a flat bundle on these. So I'm going to come back again, non-abelian Hodge theory. For each point, I can have a flat bundle. So restriction of the flat bundle to that phi bar, and then get a Higgs bundle. And that is the Higgs bundle. But that's the theorem of Hitchin, non-trivial theorem of Hitchin. Now, and his theorem is that this gives a diffeomorphism between Teichmuller space and this H naught of, sorry, I should say, yeah. And if you want to see best point, in terms of best point, it's become x naught. No, this is okay. This. So now this doesn't vary holomorphically because if you only fix an x naught, this becomes as quadratic differentials, which is a affine space, a vector space, and the Teichmuller space is like a bounded set in Cg minus C. So that cannot be biholomorphism. So this family of Higgs bundles is not biholomorphic. Because Teichmuller space cannot be isomorphic to biholomorphic. It is diffeomorphic to a vector space, but it is not biholomorphic to a vector space. So this family of Higgs bundle cannot be holomorphic. So this question, when the family of this question, when the family of Higgs bundle is holomorphic for a representation, flat connection, this has negative and positive answers in various cases. So now we let us formulate it and try to make the question precise. So S is a compact oriented surface. Oriented connected surface. Of genus G, which I take to be greater than or equal to 2. TS is a space of all complex structures on this surface compatible with the orientation. The C-infinity surface I take all C-infinity complex structures. On S compatible with the orientation. Now there are a couple of groups, actually 4 groups. I'll come. First is diff naught of S. Diff of S. Group of diffeomorphism. Diff naught S. Group of diffeomorphisms of S homotopic to the identity map. So diff naught is a connected component. This fact that diff naught is a connected component is a normal subgroup. Is a connected component with identity element, largest connected group. Now, diff X on, oh sorry, I should put a plus. If you want compatible with orientation preserving. And this is also orientation preserving, but I think let me drop the notation plus here. I will always mean orientation preserving. Whenever I talk about diffeomorphism, I mean orientation preserving. And whenever I talk about complex structure, I mean compatible with the complex structure. So diff S acts on CS. By diffeomorphism, you have a complex structure, you can pull diffeomorphism, you can pull back the complex structure, you get a new complex structure. So now, CS follows the action of the subgroup, diff naught. This is called the Teichmuller space. Space for S. And CS modulo diff S is a moduli space. Of genus G Riemann circle. So there is a quotient map because this is a smaller subgroup. There is a quotient map. Now the normal subgroups of this diff naught S, diff S. This quotient, that means group of connected components that act on this. And this is a quotient. So this is called the mapping class group in CG. Mapping class group of S. So mapping class group acts on this and this is a quotient. Let us recall a few properties which we will not need. Some first property we will not need, but it's worth saying. This is a full group of automorphisms. It's a very, very fundamental theorem of Freud. And the same Royden whose textbook you read in the masters. So this is the group of holomorphic automorphisms of this. This is like a bounded domain in E3G minus 3, but this is a quasi-projective variety. This is a much richer structure. It's like a projective variety minus a divisor, which we'll use at some point. So now what I'm trying to do is this, trying to construct this family. I've constructed the base, the Teichmuller space. I'll put the Riemann surface, family of Riemann surface on it. So that's, I have to fix a point x naught of the surface. I fix it. Now, diff, I put a 1 here for some reason, is a subgroup of diff 1 of diff S, consider all f such that consisting of all diffeomorphic f such that f of x naught is x naught. So I'm not, earlier I took all diffeomorphisms of S, now I'm taking diffeomorphism of fix a point. Now I take, similarly I now take diff one, I put the 0 outside. I earlier put the 0 inside, let me put it 0 outside. This is, you can easily understand, this is all subgroup of this such that it fixes the point, all f that which are homotopic to the identity. That means intersection basically, this diff naught and this. All f in diff 1s homotopic to the identity as that the homotopy preserves the pair, as that homotopy preserves the point x. Point preserving homomorphism, that I call this. Now, so this is a subgroup of diff and this is a subgroup of diff naught. So now, no, I removed it. Now here, let us see. So CS quotiented by diff 1 S naught to CS by diff naught S. This is a subgroup, so the map. This is a subgroup of this quotient map. Now, what it looks like? How that fibers look like? This is a family of Riemann surfaces. This is tautologically a family of Riemann surfaces. This is my XT. When the Teichmuller space is XT. So this is a parameter space for family of Riemann surfaces. The Teichmuller surface is not exactly parameter, slightly better with a marking, and is a universal family of Riemann surfaces. Similarly, you have . the universal family of Riemann surfaces on the moduli space. This is not exactly universal family because there's some isotropies and there's some, it's only in the orbifold sense in a universal family of Riemann surfaces. Now let us look at this. Recall, as I said, this is a family of Riemann surfaces, tautological family of Riemann surfaces at Teichmuller. And this is contractible. The fundamental of this is a fundamental of fiber. It's a family of Riemann surfaces basis. I've already used that, but it's fundamental. So now I take a representation of a fiber. So take any point, P naught as before. Always pi, because I use the notation pi, so I again use the pi inverse of P naught. I take a flat connection on this. That means represent pi 1 of pi inverse P naught to GLNC or whatever, any G. Let me call it G. I take a homomorphism. Now this pi 1 of this fiber is same as pi 1 of this. So I get a homomorphism of pi 1 of CS modulo diff1 S naught 2G. I start with rho. I get a homomorphism simply because these two are same. This fundamental group of is same as this because this is contractible. So I get a flat connection. Rho gives a flat connection on this because rho gives a homomorphism of total space to G. So I get a flat connect bundle on this. Now I can do the following thing, right? For each fiber, I restrict the flat connection. And for that flat connection, I get a Higgs bundle. I get a family of Higgs bundles parameterized by this family of Higgs bundle on the fibers over this Teichmuller space. Now I can ask, when this family of Higgs bundle holomorphic? One answer we know because you already checked that when this representation is unitary, by tautology basically it is this holomorphic family of Higgs bundles. And we know that some examples where it is not. So a natural question, a conjectural statement will be that the family of Higgs bundles is holomorphic if and only if the representation is unitary. So let me write down the question. And I should not have removed it because I'll need it. Question. Take any row in form pi 1, pi inverse T naught. G is GLNC or everything. Take any. This gives an element here, the homomorphism from here. So this gives a flat G bundle on yes model the universal family. Give 1 yes 0. This is a family of Riemann surface over Teichmuller space. This is called T, which is same as yes modulo diff naught S. Take any point T here. So you take pi inverse of T. Let us give a name. E nabla. Let's call it. So on pi inverse of T, you have the restriction of E nabla to pi inverse T for each T. And this gives a Higgs bundle V theta, Vt comma theta t on pi inverse of t. For each t, I have a Higgs bundle. Question: when this family of Higgs bundles Et, theta t, holomorphic. That means it depends holomorphically on t. So by a discussion, a conjectural statement will be conjectural statement. Holomorphic if and only if this rho we started with rho is unitary. So when rho is unitary, then we know already that it is holomorphic. That is tautologically. Now we'll state our first theorem. With Heller and Heller. This family is holomorphic if no, we can put it on take G to be GL to C or SL to C or something isogenous to C, for example, PSL to C. Take. Then this family is holomorphic Et, theta t is holomorphic if and only if rho is unitary. So this is indeed true SL to C. But this is not true in general, that's what I'm trying to say. Next result. Yeah, smooth, yeah. Yeah, smooth, no problem. Next result. Else in general. So that means I have to give a counter example. So now here we'll use some work of Koberza and Ramanujan. Not the Ramanujan we know about, but it's another younger, much younger Ramanujan. I should not have. Yeah. No, you don't have to say that because you take the non-orbital. Yeah, that's not if you tautology. Unitary case. No, it is much more a tautology because underlying bundle is the same bundle and Higgs field is 0, so it's automatically holomorphic. So unitary case. So the question is that is that all? Okay. Now, before I state that theorem, did I remove all this thing? Okay, so this, consider this group and the subgroup, it is subgroup of, and these are, remember this is the group of diffeomorphism which fixes the point, and these are the diffeomorphism fixing the point are homotopic to the identity map by homotopy fixing the point x naught. Now mapping class group for one point is this is again called the mapping MCG1. If again this is a connected component, so I should say this is again a connected component. So quotient is a group of quotient is a group of connected component of this. So let us call this diff1 of S by diff1 of S. This is called MCG1, mapping class group for one point in Riemann surface. Now, I deleted some things which anyway. Anyway, write it again. Yes. No, I've already have. So the universal Riemann surface, because that this is the universal Riemann surface, and now look at this. This quotient, this group acts on this. This quotient group acts on this. MCG1 of S acts because this diff1, this is a subgroup of diff1 of S, acts on yes diff1 of S not because diff1 of S acts on this. So the quotient acts on this quotient of group acts on this. And so here from that you have a map to CS to diff of S. Because this is a subgroup of that. And let us write down the quotient here. Yes. Diff1 of S, sorry, S not quotiented by MCG1. And here I can put the diff. I can only put diff and diff not, now I can put diff. So what is this? As I said, this is the CS modulo diff S is the universal family of the Riemann surface over the universe moduli, the moduli space of Riemann surfaces. And this is the universal moduli space of Riemann surface over the moduli space of Riemann surface. For each Riemann point here, the fiber is the corresponding Riemann surface. So now I'll recall the result of Koberda and Ramanujan theorem. Koberda, Ramanujan. So there exists a surface of large genus rho from pi1 of x to GLNC, SLNC. So genus of x can be large, but there are examples, and he has more fairly explicit numbers, and here also fairly explicit numbers. These are very large numbers. There are rho such that there exists rho such that now I write down the properties. One property such that 1. So what is the property number 1? Property number 1 says that you have an exact sequence. So before I pi1 of x MC G1 and M's model mapping class group. So these are exact sequence corresponding to this. This fundamental group is MCG1 because this is a contract. This is a MCG1, and this fundamental group is like MCG, and the fibers are like surfaces. So you have this exact sequence from this fibration. From this fibration, you have this exact sequence. From the long exact sequence homomorphic, you can get this. So I have a rho is a homomorphism from here to SLNC, capital N. The first property says that 1, rho extends to rho tilde. So there is a homomorphism whose restriction is this one. 2, rho is completely reducible. This is not a serious subsum. This can always be arranged. So I should not actually say this. Third is important. There exists alpha in pi1 of x element here such that rho of alpha such that the adjoint action of rho of alpha on Lie algebra of SLNC. So I'm writing SLNC. This is a Lie algebra. Has an eigenvalue whose absolute value is greater than 1. Value is strictly greater than 1. There is, let me say it again, there is a homomorphism such that it extends to this rho tilde. It is rho is completely reducible, and there is an element alpha here, such that rho alpha is an element here. Its adjoint action on the Lie algebra has eigenvalue strictly larger than 1. So this means what? This rho cannot be unitary, because if it is unitary, all the eigenvalues has to be absolute value 1. So this rho is not unitary. So now we are in the game. So look at this. Each fundamental group is like MCG1. So I have a representation of the fundamental group of this. So I have a flat bundle on this. So I have a flat bundle on this in the universal family of Riemann surface over moduli space. such that on a fiber, each fiber, it is not unitary. Rho on a fiber of the map, universal curve to the Teichmuller space. I have a flat bundle of the universal curve over the Teichmuller space, such that if I take a curve in the fiber, the representation is not unitary. But what happens to the corresponding Higgs bundle? Family of Higgs bundle. Now, most important that this is a quasi-projective variety. Universal, this is a quasi-projective variety, and this is a quasi-projective variety. This is a moduli space of curves, and this is a universal moduli space of curves. Universal curve over the moduli space. All are quasi-projective variety. And I have a flat bundle of this. So I can compactify this, anything can be compactified, and have a flat connection on the open part. So I apply Mochizuki. So I have a Higgs bundle on this. Because it's a quasi-projective variety representation, etc. But now I am not interested in the Higgs bundle on this. I am in Higgs bundle on the fibers. But now I can remember when you have a submanifold, how do I get a represented flat connection, restrict the flat connection and corresponding Higgs bundle? I just restrict the Higgs bundle. So if holomorphic family of holomorphic Higgs bundle on this, such that when you restrict to each curve, it is the Higgs bundle of that representation. By that property, that Higgs bundle, the non-abelian Hodge correspondence is compatible with the restriction with submanifolds. So here is the big universal family of family of curves. I have a Higgs bundle given by the representation. But now I am considering the restricting the restriction to every fiber and trying to get what is the Higgs bundle. Answer is very simple. It is just restriction of the Higgs bundle. So by definition, the family of Higgs bundle is holomorphic, because I have a whole Higgs bundle on the entire thing and restricting and looking at that and asking whether it's holomorphic or not. It's of course holomorphic. Because restriction of a holomorphic is a holomorphic family. But the representation is not unitary. So this gives a, sorry, I'm over the time. So this gives a counter example. Thanks, I'll stop here. Thank you.
Thanks, Indranil. Questions, remarks, comments? Maybe could you explain the very last? It was pretty fast because you felt like you were out of time, but you weren't really out of time. So you started a little bit late. So anyway, but there was this punchline at the end, right? You produced a contradiction. So yeah. Can you redo this essentially? Yeah.
I have the Teichmuller space. I have the universal family of Riemann surface. Fundamental group of fiber is same as the fundamental. I take a representation of the fundamental of the fiber. Since the fundamental group is same, I get a representation of the fundamental of the entire extension. When I start with the representation of the fundamental of this, I get a representation of the fundamental of this. I get a flat bundle on this. I want to say whether the family is unitary or family is holomorphic. The corresponding family of Higgs bundle is. I want to know whether the family of Higgs bundle is holomorphic or not. So I'm going to give a counter example. I want to produce a non-unitary representation. If it is unitary, then of course the family is holomorphic. But I want to say that there are non-unitary representations for which the family remains holomorphic. So what is the representation? I start with the one given by Koberda and what did I write? One given by the Koberda and Ramanujan. And I want to show that the family of Higgs bundles is holomorphic. I cannot do it because I cannot apply non-abelian Hodge theory to this here because this is not a quasi-projective variety argument. But remember, the flat connection he has constructed is coming extends to, that was a very important property, that rho extends to rho tilde. That means it comes from a that connection of xt modulo mcg1 is pulled back from here. And here is the moduli space. So this, that connection for which I am considering, I am to say that the family of Higgs bundles is holomorphic. I have the good fortune that this family of holomorphic, this holomorphic connection is coming from here. Holomorphic connection on this. And now here I can apply non-Abelian host theory. And there is a global, the flat connection here, so there is a global Higgs bundle. So Higgs bundles are just given by the individual curve are given by just restriction. And here it is just a pullback, because a pullback curve, it is just isomorphically going down. Right? Only the identification of the parameter space. So that's otherwise this fiber is going to fiber isomorphically. Fibers are going to fiber. So I get a holomorphic family of Higgs bundles.
Question.
Yes.
So, this holomorphic Higgs bundle on Teichmuller space, can you talk about their moduli spaces?
Yeah, we have a Higgs bundle on this. Xt modulo T is the Teichmuller space, and it is a Teichmuller space of one pointed curves. And here it is Higgs bundle is on this, but this is not compact. So if you compactify the
Yeah.
Teichmuller space, you have to go to the quotient. Sorry, moduli space
Yeah.
and MC. You can compactify the moduli space by Dellin-Mumford compactification, and I'm sure there's some there's a corresponding universal curve. I think there's a nice family of universal curve. And there you can consider Higgs bundle, but what you have to do is that you have to specify things on the boundary. What happens is the divisor that you have added, that the boundary at infinity, that neural curve. So you have to fix some parabolic data. So it will go to some moduli space of parabolic bundle on the moduli space of curves.
I see. Oh, okay.
But it has to come with parabolic structure, because you are given on the data on the open set, and you're compactifying it and extending the data. So there should be some data on the boundary, and that data on the boundary is called parabolic data. Without that, there will be too many things.
I see. Okay, thank you.
Okay, any more questions? Oh, yeah, please.
No, they don't have explicit, they have some bound. It has to be minimum at something. They don't have exactly number. Yeah.
For your theorem,
We need the abstract properties. We don't need exactly what n is. We need to give a counterexample. So
what about SL2C works and not SL3C or something else?
yeah, that's a good question. Yeah, that is, many things seems to be true for SL2C, and I think also we have some theorems which is true for SL2C, but which is not true for SLN. No, there are some subtle differences. In this context, it is.